Hey guys, hope you're all doing good and welcome to a new video. In the last class, we derived a governing equation that dictates how the temperature changes in a 1D domain where there is no external sources of heat. So this time what we are basically going to do is we are going to take a 1D domain, right? So again, you can draw it in any shape you want, but what I'm saying is along the x-axis is where the temperature difference is going to take place. So in other words, all I need is just a single point to represent that particular location, and I just need one value of temperature in that location. And obviously these are your boundary points. So now what we are also going to do is we are going to say that there is going to be a volumetric source of heat generation, right? So in this entire volume there is going to be some, and I'm just going to call this as Q triple dot, right? And I'm going to say that this is the amount of energy that's introduced in watt per meter cube. So it's very similar to how a battery would generate. But the only thing is, though the heat generation is applied to the entire rectangle, only these nodes are going to be affected, right? That's because this is a 1D problem. If it's a 2D problem, then you will have nodes throughout the area. Then those nodes will also get a share of the generated heat. So now, just like we did last time, we are going to first draw a control volume around a single node which is at the interior, and let's just isolate that node. So this right here is the x location, this right here is the x plus dx location. Alright, and just for the sake of it, what I'm going to do is I'm going to say that the area of cross section is going to be a meter square. Alright, so now the incoming heat is going to be Q at x, the outgoing heat is going to be Qx plus dx, and the volumetric heat generation is going to be Q triple dot. Now we know that the volumetric heat generation as units of watt per meter cube, and the heat flux as units of watts. So now if I basically write an energy balance, which basically says that my input heat plus generated heat is equal to the heat that actually goes out, that would be wrong because we have broken the dimensionality of the problem. So Qx as units of watt, you cannot add a quantity that has units of watt per meter cube and then expect the results to be watts, right? So this essentially says that our equation is wrong. So how do we take watt per meter cube and convert it into watts? Well, it's very simple, right? If you are able to multiply this with another quantity that has units of meter cube, then you would essentially get units of watt. And what is it that has units of meter cube? Well, that's volume, right? So what I can do is I can basically say Qx plus Q triple dot multiplied by volume of the entire control volume is going to be equal to Qx plus dx, and this is going to be correct. And volume is generally area times dx, right? So this is where our cross section area comes in, so I can retain this. And just like we looked at in the last lecture, Qx plus dx is nothing but Qx plus dq by dx into delta x. So I can cancel Qx right off the bat, and essentially what I have is Q triple dot a times dx is equal to dq by dx into delta x. Now we are going to apply Fourier's law here. Q is nothing but minus ka times dt by dx. If we take this equation and substitute it here, we would get d by dx of minus Ka dt by dx into delta x is equal to q triple dot a times delta x. So this right here should be delta x or dx, depending on how you want to call it. Now what I'm going to do is I'm going to take the area of cross section out of the derivative and also the thermal conductivity. So we will have minus Ka times d square t by dx square is equal to q triple dot a times delta x, and you have another delta x here. So we can take a times delta x and we can cancel it out on both sides. So essentially the differential equation that we have is nothing but d square t by dx square is equal to q triple dot by a. Now remember, we are going to assume that the volumetric heat generation is constant throughout the volume, so it's not going to be a function of x. So essentially q triple dot, and sorry, this has to be thermal conductivity K, right, not the area. Both of these are constants. So what we are going to do is we are going to take this, we are going to multiply right hand side with small dx before we take the integral. Alright, so integral of d square t by dx square is going to be dt by dx, and here we are going to have q triple dot by k, and there is a negative sign, right? So there is a negative sign here, so let me just carry it over here as well. And integral of dx is going to be x plus a constant. Now we can kind of do the same thing again. So I'll first multiply and then integrate on both sides with respect to dx. And since q triple dot by k is a scalar, I can take it out of the integral sign, plus integral of c1 times dx. So integral of dt by dx with respect to dx is going to be t of x, and on the right hand side we have q triple dot k multiplied by x square by 2, plus we are going to have c1 times x plus another constant. Now in the same example, so here let's call TL as the temperature on the left hand side node and TR is the temperature on the right hand side node, and let's figure out the values for C1 and C2. So when x is equal to 0, we know that temperature is equal to TL. So if you take this and solve it, you essentially get the equation T left is going to be equal to C2, right? So that's a straightforward result. Now we also know that at x equal to L, the temperature is going to be TR. So if we substitute this, we basically get TR is equal to minus q triple dot by k times L square by 2 plus C1 times L plus C2, which we know that it's TL. So I can basically say that TR minus TL plus Q by K into L square by 2 is equal to C1 times L. So in other words, C1 is going to be equal to TR minus TL divided by length plus Q times L divided by K into 2. Now there is L square here. When you divide it by L, that gets cancelled. So now that we have determined C1 and C2, so let's figure out the final expression. So T of x is going to be minus q triple dot by k x square by 2 plus TR minus TL by L plus this should be q triple dot L by 2 times k, and this entire thing has to be multiplied by x plus C2, which is nothing but TL. Now obviously there is room for simplification, but this right here gives us an expression. Now here is the interesting part. If you assume that this 1D model is for a battery, right? Now again, please remember that for a battery pack, it's better if you derive the equation in cylindrical coordinates. But the idea is, if this equation is valid for a battery pack, you can actually model Joule's heating, entropic heat generation, aging effects, mixing effects, and you can solve the equation that we had seen in the previous presentation. You will be able to compute q triple dot, and from that you can actually estimate the temperature within your battery pack. So now what I'm going to do is I'm going to show you a simple Excel calculator that I wrote to solve this particular equation. So this right here is the steady state temperature distribution calculator. So here T left is 80 and T right hand side is 20 degrees Celsius. And for thermal conductivity, I have the control set right here. So for each and every case, I can basically change the value of thermal conductivity. So currently I'm not changing it. And here you can see that this is the X value, right, 0 to 1. And this right here is the temperature. Oops. Let me just modify this. Alright, so this is the Excel calculator that I wrote to solve the equation that we just now derived. So here what I have done is I'm plotting the X position and the temperature, right? And you can see that I have 3 graphs. So the data for the graph comes from, this table, and this table. In all these 3 cases, you can see that the X vector is the same. It goes from 0 to 1, right? So the only thing that is different is the temperature that I'm plotting. So in this case, I'm plotting temperature for heat generation equal to 0, and that's the blue line. And you can see that when the heat generation is 0, you essentially get a straight line. In this scenario, we basically look at the temperature when the heat generation is equal to 50 watt per meter cube. And in this case, we have 100 watt per meter cube. And what I'm doing is I'm plotting all of them on the same graph. And you can actually see that at the boundaries, the values are the same, because that's what boundary conditions are, right? They don't change. And in the interior nodes, the temperatures are actually estimated. So the number of points that I have depends upon the number of nodes. So the number of nodes that I have used for this calculation is equal to the number of rows that you see here, which in this case, if you look at the count, is 11. So I'm looking at 11 nodes in total, and 2 of those nodes are boundary nodes, so I have 9 interior nodes. Alright, so let me summarize what we learned in this particular lesson. We looked at how to derive an energy balance equation for a one-dimensional problem, and we looked at the derivation with and without heat transfer. Now, though we did a one-dimensional analysis, this actually teaches us a lot about batteries. If you want to actually compute the temperature distribution inside a battery accurately, you just have to get the heat generation term accurately. Once you do that, you can actually use this particular equation to get the temperature distribution inside the single cell that you have. Now, yes, your accuracy would be much better, and now the right way to do this would be to derive the governing equation using cylindrical coordinates, because most of your cells are cylindrical in shape. But if you see a cell that's rectangular in shape, then this approximation would be okay. But the one-dimensional assumption would no longer work. You would have to at least use a two-dimensional temperature equation. But the thing is, the derivation process for deriving the 2D equation is exactly the same as the derivation process for 1D equation. Alright, so now that being said, let's discuss the drawbacks of the analytical method. Now, in the examples that I demonstrated, I basically took a simple 1D problem, right? But batteries, battery packs, battery modules have complex shapes, so it's going to be extremely hard to derive an analytical equation for a battery pack. In fact, it turns out that even if you're able to derive the equations, you cannot solve it by using basic techniques such as integration by parts. Alright, and that is why people use numerical techniques, numerical methods to solve these differential equations. And a process called numerical discretization is employed to convert the differential equations into a linear equation, right? And there are several methods to do it: finite difference method, finite element method, and finite volume method, right? In fact, the point-based derivation that we had shown earlier is essentially what finite difference method is all about, right? Though we did not get into it in a detailed way, you know, looking at the derivatives at a point level and then deriving an equation based on that is the fundamental concept behind finite difference method. So how are complex problems solved? So complex problems are solved by taking the original differential equations and solving them in a discrete domain. And with respect to battery thermal management system, if you want to do this, you have to learn something called as computational fluid dynamics. Computational fluid dynamics, which is often called as CFD, deals with simulating fluid flows using a computer. Alright, with that I would like to conclude this video, and I will see you guys in the next one. Bye.